Imagine peering into a cosmic nursery, a place light years away, not with your eyes, but with a telescope powerful enough to resolve a swirling vortex of gas and dust around a newborn star. In this colossal disk, countless microscopic grains of ice and rock are colliding, sticking, and growing. At this very second, they are assembling themselves into pebbles, then boulders, and then into the cores of entirely new worlds. This isn't a computer simulation or a scene from a science fiction film. This is real, raw planetary creation, and for the first time ever, we have a front row seat. For centuries, the birth of planets was a mystery confined to philosophical thought and mathematical models. Thinkers like Immanuel Kant and Pierre-Simon Laplace hypothesized that our solar system formed from a collapsing, spinning cloud of gas, a solar nebula. For 200 years, this was our best guess, an elegant theory with little direct evidence. But today, we live in a revolutionary era of astronomy. The vague, theoretical smudges of the past have been replaced by astonishingly detailed images from observatories like the Atacama Large Millimeter Array, or ALMA, and the James Webb Space Telescope. We are no longer just guessing how planets are made, we are watching it happen. In this episode, we'll journey into these stellar nurseries to witness the beautiful, chaotic, and intricate process of a planet's birth, step by step. So, what exactly are we looking at? This structure is called a protoplanetary disk, and it's the leftover material from the formation of the central star. As a giant cloud of interstellar gas and dust collapsed under its own gravity to form the star, the conservation of angular momentum flattened the remaining material into a vast, spinning plate, like a potter's wheel shaping clay. These disks are enormous, often stretching for hundreds of astronomical units, many times the distance from our Sun to Neptune. They are composed primarily of hydrogen and helium gas, but they're seeded with a crucial 1% of heavier elements in the form of microscopic dust grains, silicates, carbon compounds, and, in the colder outer regions, frozen water, ammonia, and methane. This disk isn't uniform, it has a temperature gradient, it's scorching hot near the star and unimaginably cold at its outer edges. This simple fact is the key to understanding why different kinds of planets form in different places. How do you build a planet from something smaller than a grain of sand? The process begins with accretion. In the cold, dense regions of the disk, these tiny dust grains are coated with a layer of sticky ice. As they orbit the star, they gently bump into each other. It's not a violent collision, more like a cosmic drift. Thanks to electrostatic forces, much like static cling in your laundry, they stick together. One grain becomes two, two become four, and so on. Over tens of thousands of years, these fluffy aggregates grow from microscopic specks into centimeters-wide pebbles. This process is greatly accelerated beyond a critical boundary known as the frost line or snow line. This is the radius in the disk beyond which it's cold enough for volatile compounds like water to freeze into solid ice. Since water is far more abundant than rock, this suddenly makes a huge amount of solid building material available, allowing objects to grow much, much faster in the outer disk. Once these collections of pebbles reach a certain size, perhaps a kilometer or so across, a new force takes over: gravity. These objects are now called planetesimals, the first true planetary building blocks. At this stage, growth enters a runaway phase. The largest planetesimal in a region has a slight gravitational advantage. It starts to pull in smaller pebbles and dust, not just through direct collision, but by gravitationally focusing them into its path. The bigger it gets, the stronger its gravity becomes, and the faster it grows. This rich get richer effect is incredibly powerful. As this growing planetary embryo sweeps through its orbit, it carves out a gap in the protoplanetary disk, consuming all the material in its path. This is exactly what we believe we are seeing in the stunning ALMA image of HL Tauri. Those dark, circular gaps in the disk are not empty space. They are likely the orbital paths cleared by unseen, newly forming planets, each one a gravitational titan in its own little kingdom. The frost line doesn't just speed up growth, it dictates the very nature of the worlds that will form. Inside the frost line, close to the star, it's too warm for water, ammonia, or methane to freeze. The only solids available are rock and metal. This limits the amount of building material, resulting in smaller, denser terrestrial planets like Mercury, Venus, Earth, and Mars. But outside the frost line, the story is completely different. Here, a planetary core can incorporate not just rock and metal, but vast quantities of ice. This allows the core to grow much larger, much more quickly. Once a core reaches a critical mass, about 10 times that of Earth, its gravity becomes so immense that it can begin to capture the most abundant element of all, gas. It starts pulling in hydrogen and helium directly from the surrounding disk, initiating a period of frantic growth that balloons the planet into a gas giant like Jupiter or an ice giant like Neptune. The final stages of planet formation are anything but gentle. The early solar system was not a serene clockwork of orbits. It was a violent, chaotic shooting gallery. Instead of one dominant planet in each region, there were likely dozens, even hundreds, of Mars-sized planetary embryos jostling for position on unstable, overlapping orbits. This led to a period of giant impacts. Worlds collided. Some merged to become larger planets, while others were shattered into asteroid belts. Our own moon is thought to be the product of one such cataclysm when a Mars-sized object we call Theia slammed into the young Earth, throwing a cloud of molten debris into orbit that eventually coalesced. Furthermore, the giant planets themselves likely didn't form in their current locations. Models like the Grand Tack suggest that Jupiter may have migrated inward toward the Sun before being pulled back out by Saturn, a gravitational dance that would have scattered smaller planetesimals everywhere, shaping the final architecture of our entire solar system. For all of human history, this entire story was an inference, a model built on chemistry and physics. But now, this is what we see. This is the grand reveal. The James Webb Space Telescope is not just an observatory, it is a time machine and a cosmic chemical laboratory combined. In the disk around the star PDS 70, JWST has directly detected the chemical signature of water vapor in the inner disk, the exact region where rocky planets are forming. The building blocks for Earth's oceans are present and accounted for in another solar system right now. We have moved beyond just seeing disks. We are directly imaging the planets themselves. Using advanced coronagraphs that block the overwhelming light of the parent star, we have taken actual photographs of worlds like Beta Pictoris b and the planets of HR 8799, glowing red-hot with the heat of their own formation. We can even analyze the light passing through their atmospheres. More than that, JWST has found a rich diversity of carbon-bearing molecules, including methane and carbon dioxide, in these disks. These are the very ingredients that form the basis of life as we know it. We are watching the primordial soup being stirred on a planetary scale hundreds of light years away. It's like being handed the architect's blueprints and a live construction camera for new worlds. So, what if you could watch a planet being born? The incredible answer is you can. We are living in the first generation of humanity to witness this fundamental cosmic process. Each new photograph, each new spectral analysis adds another brushstroke to our picture of creation, and it reinforces a profound idea. The formation of Earth was not a singular miracle. The same physics, the same chemistry is playing out around countless stars across our galaxy. What kind of worlds are taking shape in the dark right now? What new discoveries await us in the next data release from Webb? The age of cosmic discovery is just beginning. What do you think is the most exciting unanswered question about planet formation? Let us know in the comments below. And if you found this journey as awe-inspiring as we did, be sure to subscribe and join us again on Docilare Cosmos.